So, are you ready for the next talk? Sleepy audience. Are you ready for the next talk? I didn't hear you. Are you ready? Perfect. Thank you, God. I needed to. I was sleeping too. Perfect. Not for the talk, but I didn't drink so much coffee today, so I'm a little bit sleeping. So now we have this talk about sustainability. He is Sohan Maheshwar. Probably is misspelled, sorry.
No, it's good.
Perfect. He is a developer advocate lead at Fermion. We talk a little bit later before the talk, and he said he's a professional frisbee player. He plays in the national team, but he said he didn't get paid.
So not professional.
That's not professional. Yeah. But you are in the national team, so that's good. Yeah, we have Olympics too. Yeah, open source Olympics Day. Yeah. Perfect. So someone will talk about a greener and cost-effective cloud and frisbees with serverless WebAssembly. The stage is all yours.
All right. Yeah. Thank you so much.
Thank you.
That was definitely a unique introduction. It is true, I'm not a professional frisbee, I just like playing as a hobby. I came from a frisbee tournament on the weekend in Valencia. They had like 40km/h winds on the beach. Felt like I was on the set of Dune 2. Was not fun. Anyway, the weather here is a lot better. Quick introduction, my name is Sohan. I live in Amsterdam, and I work for a startup called Fermion. Spent 6 years at Amazon Web Services before this, so I've been in the cloud space for a while. And any people who use WebAssembly here, just out of curiosity, are familiar? Oh, very few. OK, perfect, because I'm going to set some context on what WebAssembly is. But the main focus of today's talk is how you can be greener and more cost-effective with a combination of serverless and WebAssembly. So I'm so happy to be here. It's my first time in Florence. So it kind of sucks that I have to start with some bad news, which is the Earth is burning. Climate change is real. It is true, right? And if you follow the space, you'll know about the Paris Agreement, which says that all countries have decided to reduce the global temperature by 2 degrees Celsius, which is easier said than done. And for that to happen by the year 2050, we have to cut global emissions by half in 2030, which is not very far from now. That seems like a tall task, so I think we all have to do our part. Now, the interesting thing is that the Green Software Foundation actually says that the software and technology sector causes about 3% or maybe even more of the world's global carbon emissions. And by contrast, that is about the same amount as that of the aviation industry, which is pretty mind-blowing if you think about it. And this is only going to increase in the years to come because software is at the heart of everything that we do. So it is quite a big deal. So I think it's high time we actually take into account sustainability in technology. Now, there's an old saying that says, if you can't measure something, you can't improve it. So how do you really measure sustainability, or how do you measure your carbon emissions in the cloud? Well, the Green Software Foundation, and maybe I can stand here. Yeah, I can stand. The Green Software Foundation actually has this formula called software carbon intensity, which gives you a rough metric as to what your carbon emissions are in the cloud. So the formula is C per R. The C stands for carbon, and the R is a rate. Now this part is important because this is not an absolute number. They won't tell you, oh, this is your carbon emission. It's per something that you do repeatedly in the cloud. So for example, it's per API call or per machine learning training run, right? So it is a rate. the C can be expanded into O plus M, right? And I promise the math ends here. I'm not a big fan of math, but it ends here, right? So O stands for operational emissions. So for software to run on, say, this laptop takes some electricity via the CPU, the memory, the motherboard, and so on. So the carbon taken by that is the operational emissions. The M is an embodied emission. Now, to make this laptop, there was a factory, there was an industry, there was a supply chain to get all those parts together, all of that combined, and a fraction of that was for my laptop, right? So that is the embodied emission. Now, the same thing applies to the cloud, where you're thinking about the hardware required for a data center in the cloud. So the operational emissions for that and the embodied emissions for that. So this is the software carbon intensity of any workload in the cloud. Now, the Green Software Foundation has a recommendation of 3 things that you can do to be more sustainable when it comes to writing software, right? So first one, they say be energy efficient, where you're using less electricity to perform the same function. The second is hardware efficiency, where you use less amount of hardware, again, to perform the same function. And the third is just being carbon aware. This one's interesting. So if you use something like AWS or Azure or Google Cloud Platform, just by shifting your region, say from Asia to Europe, makes you more carbon aware, because how they get electricity sources in Asia differs from how they do so in Europe. So for instance, in Europe, in some regions, there are more renewable sources of electricity. So if there's a workload that is non-critical or it doesn't have data residency requirements, you can just shift it to, say, a Europe data center, and you're already a little more carbon aware. The reason I put up this slide is that anything that comes up after this slide, I want you to think of how it is more energy efficient or how it is more hardware efficient. And the focus of today's talk is serverless and WebAssembly, and how it's both energy and hardware efficient. Now, I asked if people had used WebAssembly. Didn't see too many hands, which is perfect, because a small context set about what WebAssembly is and why it's a big deal. So the boring answer is it's a simple bytecode format. Now, for computers to understand programs, you have to have a low-level instruction language, and that is a bytecode format. The long version of this history is sometime in the mid-2010s, I think around 13, 14, a bunch of browser companies like Mozilla, they got together to create this because they needed something that can run cross-browser, that could compile from many different languages, was more secure, was lightweight, and was very portable, right? And they came up with something called WebAssembly. And companies like Adobe, Shopify, Figma, they still use WebAssembly in their front ends, right? So as the name suggests, it was meant for the browser. And it was designed from the ground up, right, to be portable as a compilation target. So you could write code, even now, in Python, JavaScript, Go, Rust, Zig, C, C++, name it, you can write code in those languages. It compiles to a bytecode format, and that can run anywhere, right? So, and when I say anywhere, you can compile it once, and this could run on different types of architectures, like like Intel or ARM or anything else. It could run on different operating systems, like Mac and Windows and Linux. It could even run on your Raspberry Pi, for instance, right? Because it was designed to be so and so. And any place that has what is called a WebAssembly runtime can run a WebAssembly app. If I say the word Wasm, or if you come across the word Wasm, it's just short for WebAssembly. Now, the interesting thing is, it was designed to be like portable, secure, lightweight, all of that. And it was designed to be run in the browser. But people were like, hold on, this might make sense if you run it on the server side. But there were no access to things like files and file systems, which is what you need in a server. So in around 2019, there's something called WASI that was introduced, which is WebAssembly Systems Interface. And again, basically, it allowed you to run WebAssembly outside of the browser. So it gave you access to operating system features like files, file systems, networks, sockets, random number generators, and so on. And now you could run WebAssembly on the server side. And the great thing was this was independent of browsers. You don't need a SpiderMonkey or a Chromium or V8 or whatever to run this. You can just run WebAssembly on the server side, and it extended the sandboxed model of WebAssembly, which means it is secure by default. Just to give you a sense of how it looks, you write code in any language, you compile it to something called a WebAssembly format, or .wasm, and any machine that could run a WebAssembly runtime can run that. And a runtime is designed to be run in multiple architectures, OSs, and so on. So I'm going to show you a quick demo using an open source tool called Spin. Now this is a framework to develop WebAssembly apps. It's completely open source, supports about 15 plus languages. We have Discord channel, CLI, stars on GitHub, all of that. And I'm going to show you simple hello world, right? So nothing too complicated, because we'll get warm and fuzzy feelings when we see hello world. So I'm just going to show you that. I'm going to keep it like real simple. So, all right. So I've installed the CLI already, and I'm just going to say spin new. So what you can see here essentially is a bunch of, is this left or right? No, yeah. On your left, a bunch of triggers. So you have a trigger like HTTP or Redis, or maybe even a queuing service or MQTT. And on the right, you have a bunch of programming languages, right? So like you can see C, JS, PHP, Rust. All of these are the languages supported by Spin, and hence WebAssembly. I'll just choose Rust for now, because I heard people talk about Rust in the speaker room, because why not? And I'll just call it OS day, description. A path is the path that will trigger this particular application, right? I'm giving it the default, which means it will trigger it in any way. So I'll do that. And oh, I hope you can see it at the back, sorry. Let me just increase the text size. And I will open this in VS Code. Now, anyone here familiar with serverless or has worked with serverless before? Like Azure, Functions, Lambda, quite a few. Excellent. I'll give you a couple of slides about that. But what you need to know about serverless is it's completely event-driven, right? So you have an event, a function is spawned, and you send a response. So in a sense, it's a request-response model. So here you can see there's a request coming in, and there's a request coming out. Let's change that to OS day, right? That's it. Simple request in, something happens, request out, super lightweight. All right, so I will build this. And essentially what happens is, yeah, this program is built. It's Rust, so a bunch of crates are being built. And if you look at this program, there are only two things you need to know. One is your Rust file itself, which does the parsing. The other is this, which is an application manifest of sorts, which has something called a component, which we defined, which is your WebAssembly module or component. And as you can see here, with the security that I mentioned, right, you have to give access. If you're making a HTTP call, you have to specify it. If you want a file to access this module, you have to specify it. If you want this module to access a file, you have to specify it, because WebAssembly is sandboxed by default, right? Think of all the other ways you've programmed in the past where you have to specify what is allowed and not. WebAssembly by default is sandboxed. So I'm just going to do spin up, which locally spins this in a local host for you to test. And I can write a simple curl, right? And you can see hello OS day. So that is a very simple hello world type example to show you how the thinking in building WebAssembly is, right? You're writing code in the languages you like, which converts it to a WebAssembly format, which is now running here. I can take the same thing and push it to a cloud or a Kubernetes cluster, and with some configuration, of course, this same app will run. So going back to the slides. Now, there are 4 things that really make WebAssembly great and ideal to run on the server side. And I again want you to think of being energy and hardware efficient in this context. So one is binary size. This hello world example that I showed you is just about 2 MB. The HTTP API is about 2.3 MB if you just in time compile it. You can do ahead of time compilations where you're doing optimizations for the hardware, and bring that down to about 1.1 MB. I can show you that file as well. So if you do, let me see now. Sorry, target, right? I think it's LA, sorry. Yeah, you can see this Wasm file, it's 2.3 MB right here. And honestly, you can take a look at how bytecode format looks like. I can't understand any of this. If anyone can, good for you, I guess. But this is the bytecode format, right? Yeah, sorry. So it's essentially just a simple 2.3 MB file. And think about it in the terms of the programs that you've built in the past, right? Like we showed a simple Python Flask app, which did hello world. And the size was, this was a Docker file for that. The size was about this. But the same thing using WebAssembly was just that small thing, right? Like we did a small benchmark. You're seeing a difference from like a 23 MB file to a 550 KB file. And again, think about it at scale when you're building really large workloads about how you can be more energy efficient by doing something serverless in WebAssembly. The second is the time. WebAssembly was designed ground up to have near native times. You, of course, won't get native performance, of course, but in our benchmark with Rust, we saw that it was about 2.3x slower than native, which is a very acceptable speed compared to other frameworks out there. In terms of portability, you build this once, you can run that WebAssembly file anywhere. I will speak a little later about how this helps with, again, being more carbon aware and being energy and hardware efficient. And as I mentioned, this is not directly related, but security is one of the key features of WebAssembly itself, right? As you saw here, any access in or out of for this WebAssembly module has to be explicitly given. So you have like really granular access to this, again, as opposed to other frameworks where it was inverted, where you had to specify things not to have access. So just going to stand up again. Now, that was the WebAssembly context setting bit. Quickly, I think we're all familiar with how cloud computing has evolved, right? Any older folks in the audience, such as myself, we remember the days of a server room, where there was this one room, you had a server, you had an air conditioning, no one was allowed to go in there. It wasn't as energy efficient, of course. But then we moved on to cloud computing, where we virtualized things. And you didn't have to take care of the physical hardware itself. And then we moved to the age of containers, which helped us focus a little more on writing the app. But still, with containers, you have to keep a container running, even though you might not have too many processes that hit in the container every time. And then we moved to serverless, which seems to be very popular, and rightly so, where you as a developer, you just write your business logic. You don't care about scaling up, scaling down. The cloud provider takes care of that. And you can focus just on purely business logic. So serverless is gaining popularity. And again, just to context set, it can either mean something that is a short-lived event-driven function. So you say, do this one thing, it does that one thing, and it stops. But it's also a development model, right? As programmers, we don't have to think about maintaining server daemons or updating software and things like that. I'm only focused on writing my code. And this is great because as a dev, I just want to write my code, but at the same time, I can scale faster and I get more bang for my buck. It's been cheaper, you have better utilization of hardware, and you're saving costs as well. The key thing for me about serverless, or to really understand the serverless, is to understand a concept called multi-tenancy, right? Having many tenants in the same piece of hardware. Or a very crude analogy is, instead of having one massive house with like 10 floors, you make an apartment where multiple people can live in that same space. So you have many tenants in the same space. Now, multi-tenancy is actually a very interesting concept because you need multiple independent applications that can run on one piece of hardware. The trick here is that these applications should not be related to each other in terms of usage, because if one spikes and all spike, then you're not going to get value out of that. At the same time, you shouldn't intentionally be able to affect another tenant as well, right? All of these should be random. The interesting thing is the value of a system, right, in this case the hardware, is actually based on your long-term average traffic that is running on that piece of hardware, whereas the cost of running that system is based on short-term peak traffic. Now, what does this mean? And if you want to read more about this, check out this blog, brooker.co.za. He's one of the early authors of EC2 who now works in the Lambda team. Very excellent blog, a great resource as well. I'll explain this via a graph. Right? So this is a system with two tenants. You have function A and function B. You can see the two graphs here. Their sum is this dotted line right here. Now, as cloud engineers or as DevOps people, what do? We look at the peak, right? These peaks, and we say that's what we are really building for, right? We are building for the peaks. The problem is the peak is here, but the average is here at the bottom. For you to get maximum value out of a system, you need to bring this peak to average ratio as close as possible, right? Because most of the time, all of this is not being used. So as you can see, this ratio is about 1.7. The minute you add two more tenants to the same thing, your peak goes up, but look at the average versus the peak, right? The ratio is about 1.26. So you brought the value down because you've added more tenants to the same piece of hardware. And the additional second order effect, which is good for us, is all of these functions now can handle a higher peak as well, just in case you need it. The good thing is WebAssembly actually allows you to add more and more tenants to the same piece of hardware because it is so lightweight and so it takes less memory and you can scale to 0 in no time. In the early days, you could run, a few apps on one piece of hardware, but now with serverless and especially using WebAssembly on serverless, you can really pack and have dense, right? Have density in your hardware. To give you another analogy, think of how atoms and molecules are packaged in gases versus liquids versus solids. Right? In a solid, you have really densely packed molecules, and that's how you can pack a piece of hardware with serverless functions because WebAssembly is so lightweight. There's another interesting paper that I recommend you all read. It's by the team that built Firecracker. Firecracker is the VM that Lambda uses on AWS. So they defined 6 characteristics of an ideal serverless unit. First one, they said isolation. Like I said, you could run multiple functions on one piece of hardware. The 2 was overhead and density, where you can run thousands of functions on one machine without wasting CPU and memory. The 3rd was performance. Of course, we want near native. Fast switching, this is an interesting one, where you have the ability when a function gets an event to start that function, process something, and then shut it down. And to have a quick start and a cleanup of functions. And the last one was the second last one was the ability to overcommit resources. What if one of the function gets a lot of traffic, it goes viral? Can you commit more CPU and memory? And of course, the last, we need compatibility, right? As devs, we have our favorite libraries, our favorite frameworks. It needs to be compatible. So we did a quick benchmark between a micro VM like Firecracker and WebAssembly. These are the numbers we saw. Isolation, both are already sandboxed, so that's great. WebAssembly by default, micro VMs via the Firecracker virtual machine. This one's interesting, right? If you look at overhead and density, micro VMs were able to run about thousands per node with 48 core, 382 GB RAM, and 3360 GB disk. But because WebAssembly is so lightweight, you could do that with only 8 cores and 32 GB, using just a 100 GB disk, right? Again, because of how lightweight WebAssembly is. Performance got near native from both, so that's great. This one, I think, is the one where tools such as Lambda and Azure Functions don't perform well. Every time Lambda function invocation happens, it takes anywhere between 125 milliseconds and 250 to 300 milliseconds to start. Because that function has to start, the program has to start, it executes, and then comes back. Because WebAssembly is so lightweight and has a reduced instruction set, you can actually do that in less than 1 millisecond. Right? There are enough benchmarks out there, and you can scale back down to 0. The interesting thing is what people do to stop this from happening is to keep something called warming your instance, right? So every 1 minute or so, you send a request to your Lambda function to keep it warm. That is a viable strategy, but that cost is borne by us, right? And again, it's neither energy or hardware efficient. With soft allocation, we know the big three cloud really does well in that because they can oversubscribe up to 10x. WebAssembly is new, so we don't know. It's untested in production. Hopefully, we will see this in this year or by half of next year as to how it would work at like oversubscribing. And with compatibility, like I said, WebAssembly is OS architecture agnostic, so it doesn't matter. You can run it anywhere. Fairly similar with microVM, but it's Linux and KVM only. I have a demo which I don't know, how much time do I have left? Is this a video record? 5 minutes. Okay, I'll skip this demo here because I need to talk about this article, which literally came out this week. As you can see, it says March 4th. Those of you all, anyone Kubernetes users here, I'm sure most of us are in some way or the other. The big problem with Kubernetes clusters nowadays is not the fact that it's not cost effective. One of the reasons Kubernetes came out was because you could handle costs, but there's so much over-provisioning of Kubernetes clusters that's happening, right? Again, this week, this article has come out. Cast AI did a survey with a bunch of their customers and the Kubernetes ecosystem. They found the average CPU rate was only 13%, right? Utilization is low, again, because we are trying to design for the peaks and not the average. And this is a big problem. Even if you look at Kubernetes clusters with 30,000 or more CPUs, they reached about 44% utilization. But again, that's a very small percentage of Kubernetes clusters that have that many CPUs. Same story with memory utilization. And here's the thing, this is very bad for the environment. You're being really hardware inefficient by doing this. And the reason is, it's very counterintuitive that people think an idling CPU actually does not consume electricity, but that's not the truth. In scientific papers, they have said that it could consume anywhere between 30 to 60%, even though a system is idling. And there is a non-proportionality of energy consumption, right? Again, this is counterintuitive, but the more you use the system, the more value you extract from it. So rather than keep it idling, you want as much utilization of that system. And luckily, WebAssembly allows us to do that. In demos, you can see spin WebAssembly demos scale to 100% CPU utilization and back down to 0 because of how WebAssembly really is built. And these cloud optimizations, it's good for the environment, it's good for sustainability, but almost always it's going to be a reduced cost for you as a user or a company, right? So that's a benefit that we all can get behind. Really, the story is, I think, choosing the right serverless solution. Again, in this paper on Usenix, you can see that more than 80% of Azure functions are invoked once per minute or less. And a large chunk of why that's happening is to keep your Azure function warm, just to reduce cold start times. And that is very energy inefficient. It's also not cost effective, right? I think WebAssembly solves for that. And it's like that quote says, it is keeping these applications warm, these costs are prohibitively high. I think the industry is sort of realizing this is a problem. You can see a lot of articles about utilizations, about cloud repatriation. Meta also launched a serverless solution recently where they claim about 60% utilization. It's just that it comes with a vendor lock-in, but when using WebAssembly, you can run it on any cloud, right? You can run it on your own Kubernetes, you can run one function on Azure, one on Lambda, all of that. So it's pretty cool. And in the future, this was just launched a couple of months ago. It's called the component model, where because WebAssembly supports so many languages, you can actually write an app in multiple languages. And that sounds weird, but it's actually live, test it out. Go look at the component model where your JavaScript app can get a YAML parser written in Rust and a date formatter written in Python, all working together, right? Because of how componentized the WebAssembly ecosystem is. So you can write a WebAssembly module that exports a function, and this WebAssembly module can be like, hey, I need that function. let me export that, and you create something new, right? So it's an idea of componentized applications, and this really helps because think of a build file like this where you have a bunch of operating systems there, a bunch of Go versions there, and this is how we package and do our CI/CD, right? Or even here, there are multiple architectures that we're actually packaging and our CI/CD, and imagine this at scale. Now again, this is not energy or hardware efficient, but with WebAssembly, your build file is just the one Wasm file, your test is just the one WebAssembly runtime, and well, WebAssembly components are already packaged in a way. So think of how much more energy and hardware efficient you'll be. Anyway, I'm almost out of time. So yeah, for next steps, maybe build your first WebAssembly app, try it out, see how it can help within your organizations, and also talk about sustainability a little more. I think as technologists, we need to start that conversation. So start that soon. And yeah, I'll be around for any questions. Hope you learned something new today. Enjoy the rest of the conference. Thank you.
Thank you. Thank you, Sohan. Thank you. If there is any question in the room, okay, perfect.
Thank you. Interesting talk. So if I understand correctly, adopting this functional service model can lead developers to these bad behaviors of keeping functions alive, like refreshing them because they have a slow boot up time. And in my experience, maybe this is not only dependent on the runtime, Lambda versus Fermion or Wasm, but it's also because of dependencies of the application, like loading the libraries, connecting databases. So wouldn't it be much better than at this point running long-standing services in EC2 instances, for example?
Yeah, so I'm going to give my favorite answer in tech, which is it depends. I think it really depends on the sort of use case, right? Like, I know somehow serverless databases, for instance, because you're doing so much caching and all of that is maybe as thing as just running a database on like an EC2 instance. For things that are more like web trigger, that sort of thing, where you need something spawn quickly, run, and shut down, I think the serverless WebAssembly is perfect, right? So it really depends on the sort of use case. For things that are very ephemeral, that you need something very quickly to start, do something, and shut down, I think this is, more suited.
Thank you.
Other questions?
Hi, thanks for the talk. It's a bit hard. My question is a bit large, maybe a bit wide, but talking about how the world is moving, even the processor makers who are making literally a war between each other, telling mine is faster, it's faster, and we're engaging, I don't know, 300, 400 watts for CPU every time. And how do we mitigate this kind of maybe advertising, and how do we go against it while I know the generation under us are constantly bombarded by this kind of mentality? And I know it's not only about our kind of job, maybe when we do programming or whatever with our applications, but I think it's very important to try to find a way to oppose this kind of thinking, maybe, and it's hard to do that even in our environment. And how would you help me do that?
Yeah, I think that's a very valid sort of thought to have in general, right? Because I think, especially at the rate at which technology is moving, you're just bombarded with all of these things. Speaking from a WebAssembly point of view, the good thing is it's a technology that WebAssembly is a technology that's not tied to a particular corporation. It's a general language, right? Like whatever, like Python or HTTP or whatever. So having that framework of not being really locked into a particular corporation and then having to switch, whereas something like this gives you the opportunity to be in the place that you already are or explore a new place, and then do, of course, your own optimizations, I think is a big deal. And especially given that we are all in the open source space, something like this makes, I think, a lot of sense, right? As opposed to a software that is like extremely commercial, that switching out of is not as easy, right? And the cost of switching is almost as much as the costs you will incur by sort of continuing. So yeah, I really think having that sort of mindset, I think helps, yeah. I think there was one question here.
There are questions, perfect.
Thank you for the talk. You made it look very easy to use WebAssembly, but I want to know if there are some, or if you can give us some pointers to what is the bottlenecks of introducing WebAssembly in a team of maybe junior devs.
Yeah. So from a coding point of view, I don't think there's any bottleneck because you can write in the language you're already writing. You can deploy in the place you're already deploying. Where there is evolution happening is in the sense that WASI, which helps us run on the server side, launched Preview 2, but there isn't support for something like sockets yet, right? There isn't support, there just came support for streaming data, right? So there are some of the things that we use, like say on a day-to-day basis, which is being added to the framework and to the protocol right now. This will improve in like 6 months, of course, but it's not at that stage yet where you can be like, all of these things that I currently use on AWS, I will get with WASI, right? At the same time, sometimes languages also have to add support for WebAssembly. Like how Python works is, it's a compiled language, right? So someone handwrites some of the Python features in WebAssembly. It's compiled in a WebAssembly module and put. So if Python releases a new like feature, that has to be added to the WebAssembly spec as well, right? So those are some of the places. Language support is getting better, and support in WASI is getting better, so it's in a good state of evolution, yeah.
Thank you.
Thank you. I don't know if there is any other question, or are we going to take a little break because it's kind of hot right here. I think it's because of me, of course. I'm kind of hot, yeah, no, I don't think so. But I think we take a 10 minutes break just to open the doors and keep the air coming in. And of course, here is your trophy. And thank you to be here. And if you have any other question, you can find him somewhere here. Thank you.